Hi, in this video, I will continue with section 3.4, polynomial functions, graphs, applications, and models. So this is a summary of what we did last time. We learned that if n or if f of x is a polynomial function of degree n, then f has at most n zeros, which can be real or complex. And the sum of their multiplicities is n. The sum of the multiplicity is going to be equal to the degree of the polynomial. And number two, the graph of f has at most n minus 1 turning points. A second degree polynomial, the graph is a parabola, so the turning point is at the vertex. A third degree polynomial has at most 2 turning points, and so on. But it can have less than that. It can have less than less than 2 turning points. And the best example is x to the third power. It has no turning points. So today we're going in this video, I'm going to talk about the n behavior. We're going to be using the following notation. The notation is going to be something like this: x, right arrow, infinity. So this will stand for x approaches infinity. Or x increases without bound. And we're going to use the notation x approaches negative infinity, x right arrow negative infinity, to denote that x approaches minus infinity or negative infinity. This means that this will mean that x increases without bound in the negative direction. Okay, so I'm going to bring back some of the graphs with it in the last video. Okay, so I'm finding this. Okay, so let's take a look at this graph that we did. In the last video, we went over the zeros of that polynomial. Okay, so as x approaches infinity, one way to say it works is that the graph rises to the right. In more mathematical terms, as x approaches infinity, the graph approaches infinity. And the graph falls to the left. So as x approaches negative infinity, f of x approaches negative infinity. So when x keeps moving to the left, y keeps falling. And when x when x increases, when x moves to the right, y increases. And another graph that we mentioned, I'm copying that. So that one, as x approaches infinity, f of x approaches negative infinity. So the graph falls to the right. And as x approaches negative infinity, as x moves in the negative direction, y increases. So f of x approaches infinity. Okay, so here's a summary of the end behavior. The leading coefficient gives you valuable information. So I'm going to copy the first two parts. Okay, so I'm not going to copy the figure. I'm not copying the figures. Just this part of the just this green box. Suppose that ax to the n is the dominating term of a polynomial function of a degree. That is, the leading coefficient is a, and n is a degree. If a is positive, then as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x approaches negative infinity. So here are the first two situations. We have the graph. Whenever a, the leading coefficient is positive and the degree is odd. So the end behavior will be that as x approaches negative infinity, f of x approaches negative infinity. And as x approaches infinity, f of x approaches infinity. And we don't know what happens in between. There might be turning points, there might be zeros, there may be other things, but that's going to be the end behavior. And the symbol is going to be with these arrows. And second case scenario, if the leading coefficient is negative and the degree of the polynomial is odd, then f of x approaches negative infinity. Let's say f of x approaches negative infinity as x approaches infinity. So when x approaches infinity, f of x approaches negative infinity. There might be some things in between, some turning points or some zeros, some intercepts. And as x approaches negative infinity, f of x approaches infinity. And that's going to be the notation in general. And when the degree is even, let's copy the next part. That's a continuation of that green box. Suppose that ax to the n is the dominating term of a polynomial function of even degree. If a is positive, then as the absolute value of x approaches infinity, f of x approaches infinity. So let's say you have the graph of a polynomial. A polynomial whose leading coefficient is positive and the degree is even. So the absolute value of x approaches infinity. That is, as x approaches negative infinity, f of x approaches infinity, and as f of x, or as x approaches infinity, f of x approaches infinity. In between, there might be some other things, like some turning points or some zeros. And the last case scenario, if the leading coefficient is negative and the degree of the polynomial is even, as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches infinity. And there might be some other things like some turning points, but or they mark this one. It may not have any y-intercepts, so we don't know. It may even be something like this. We don't know, but we know for sure from the leading coefficient and the degree, we do know the end behavior. So without trying to graph the function, just by using the leading coefficient and the degree, we're going to determine the end behavior. Okay, so there it is. Okay, so I'm going to copy the directions. On page 352. To describe the end behavior of the graph of each polynomial without using a graphing calculator or without trying to graph the function. Okay, let's start with number 22. So the leading coefficient is -1, and the degree of the polynomial is 3. So that's even degree, odd degree with negative leading coefficient. The corresponding diagram will be this. It's going to be rising to the left and falling to the right. Number 24, the leading coefficient is 4, and the degree of the polynomial is 7. Okay, so odd degree, positive leading coefficient, the end behavior will be rising to the right, falling to the left. 26, the leading coefficient is 10, which is positive, and the degree is 6, which is an even degree. We know the end behavior, we don't know what happens in between. So even degree, positive leading coefficient is going to rise to the left and rise to the right. And number 28, we have the polynomial is in increasing form. The last term is the leading term. So the leading coefficient is -10, which is negative, and the degree is 4. So that's a polynomial of even degree with a negative leading coefficient. The graph is going to fall to the left and fall to the right. Yeah, we don't know. This is not necessarily a turning point. Okay. Okay, and the longest part of this section will be graphing techniques. So I will copy the box on graphing techniques. That's page 344. Let's suppose you have a polynomial function of degree n. So to sketch the graph, follow the steps. Start by finding the real zeros. That is, if you can, write the polynomial in factor form. Those are going to be graphically, those are going to be the x-intercepts. If it has complex zeros, a complex zero is not an intercept. Then find the y-intercept. Evaluate the polynomial at 0. So the constant term will correspond to the y-intercept. And finally, use end behavior, whether the graph crosses, bounces on, or wiggles through the x-axis. That's going to be given by the multiplicity at the x-intercepts, and select selected points as necessary to complete the graph. Okay, so in the last examples, we're going to graph polynomial functions. And I'm going to copy one more box on page 346 about the factors and the zeros. Okay, so that's page 346. F is a polynomial function, and c comma 0 is an intercept of the graph of y equals f of x, then c is a zero of f. Not only that, it's going to be a real zero. C is a solution of f of x equals 0, and x minus c is a factor of f of x. So all these three are equivalent. Now, if c is a complex zero, it's not going to be an x-intercept. So we are going to graph the given polynomial functions in the following examples. We are going to graph each polynomial function, and factor first if the polynomial is not in factor form. If you have it in factor form, you can quickly determine the zeros. We are going to start with number 38. Those are on page 352. Okay, so we need to factor by grouping. We're going to write in factor form. That is going to give us the x-intercepts. And in order to write in factor form, we need to factor by grouping. So that's a topic from elementary algebra. We're going to group the first two terms and the last two terms. So we're going to group them. Once we group them, we're going to identify the common factor of each group. So the common factor of x cubed and x squared is going to be x squared. That's how you factor the first group. The common factor of the second group is going to be negative 36. So minus 36x minus 36 factors as minus 36 times x plus 1. Okay, so now x plus 1 is a common factor. It's a common factor of x squared and negative 36. So we can undo, or we can do the distributive property backwards. And x squared minus 36 factors as x minus 6 and x plus 6. Okay, so we were able to write this polynomial in factor form. I'm going to write them in order. X plus 6, x plus 1, and x minus 6. So that's the same polynomial as we began with. Only the first one was in general form, and this one is in factor form. The good thing about the factor form is that now you know what the zeros are. So the 3 zeros, that's a polynomial of 30 degrees, so it has 3 zeros of multiplicity 1. The zeros are -6, -1, and 1. They all have multiplicity 1. So if those are the zeros, the x-intercepts are -6, 0, -1, 0, and 1, 0. So far. Okay, so we know the x-intercepts of the polynomial. We can also determine the y-intercept. If you notice, f as 0, you evaluate this polynomial as 0, we have 0 plus 0 plus 0 minus 36. So I'm just going to write like this. The constant term is the only one that doesn't depend on x. So the y-intercept is 0, -36. Also, the leading term is x to the third power. So the end behavior with that, that's a polynomial of 4th degree with positive leading coefficient. The leading coefficient is 1. So the end behavior is rising to the right, falling to the left. So we're going to do something similar to what we did with when solving quadratic inequalities. We have a good amount of information now, but we're going to, we know the end behavior, we know the intercepts, and we're going to use additional points to verify whether the graph is above or below the x-axis. Also, we know something else. We know that the zeros have multiplicity 1, so they will cross the axis. They won't wiggle and they won't bounce. Okay, so the x-axis. So the real zeros divide the x-axis into 4 intervals. The 4 intervals are, if the zeros are -6, -1, and 1, those zeros will divide the x-axis into 4 intervals, -infinity to -6, -6, -1, -1, 1, and 1 to infinity. Okay, so I'm not doing a lot of details, but we know what the intercepts look like. The intercept will be -6, -1, and 1. So they are going to divide the x-axis in those 4 intervals. And we're going to use a test value inside each interval. So remember that f of x, we started with f of x equal to x cubed plus x squared minus 36x minus 36. That's in general form. And in factor form, that was x plus 6, x plus 1, and x minus 1. Okay, so we're going to evaluate the function inside each interval. We're going to make a table. We did something like this before when solving quadratic inequalities and rational inequalities. In each interval, we are going to pick a test value. We are going to determine the value of f, the sign of the value of f, and finally, whether the graph is above the axis or below the axis. So we know where the function becomes 0. So inside those test values, if the function is positive, at one point it's going to be positive everywhere in that interval. It cannot go from positive to negative before becoming 0 first, or negative to positive. So let's start with negative infinity to 6, to negative 6. So the test value I can think of is negative 7. If you evaluate f at negative 7, I'm just going to write the answer. It's going to be negative 78, which is negative. If it's negative, the graph is going to be below the axis. And it's not only going to be negative at the negative 7, it's going to be negative at every point in that interval, negative infinity to negative 7 to negative 6. It's not going to become positive before becoming 0 first. From negative 6 to negative 1, I'm going to take negative 2. So I'm just giving you the answer again. F at negative 2 is going to be 36. And the sign is positive. So the graph is going to be above the x-axis. In the interval negative 1 to infinity, we have negative 1, 1. The test value is 0, and we already knew that the y-intercept was negative 36. So the graph is below the x-axis. And the last interval is 1 to infinity. We're going to evaluate the function at 2. F at 2 is 100. Sorry, that was, oh, I made a mistake. That was negative 1, 6. Let's see what I did. Okay, I see what I did. Yeah, sorry, that was a 6. And that was something I had done before. So that was a 6. So when I factored it, I got 6. So let's clarify that. Yes, so I missed that part. So that was my mistake. And there was a minus 6. So let's keep the colors consistent. And then we have it, that should be a 6. So this one is not correct. The rest of the points were. So in the interval 6 to infinity, we're going to evaluate at 7. F at 7 is 104, which is positive, and the graph is above the x-axis. Okay, so now we can draw the graph. We know the signs. And I'm not very, well, I won't be very, well, the scale is not going to be the best one because the y-intercept is 0, -36. But I do know the x-intercepts. Okay, so we have that. And well, it's going to be hard to graph the y values, but we know what the intercepts are. We know that the intercepts are -6, 0, -1, 0, and 6, 0. We know that the y-intercept is 0, -36. Now the scale is not the best one, but we know the y-intercept, and we also know what happens above or below the axis. So we know that in -∞ to -6, the graph is above the x-axis. And -6 is a 0 multiplicity 1, so it's just going to cross. In -6, -1, the graph is going to be below the axis. Oh, sorry, well, that's below the axis, of course, so it's going to go this way. Between -6 and -1 is going to be above the axis. I don't know exactly where is the turning point. If you take calculus, you'll learn methods for determining those turning points. Between -1 and 6, the graph is going to be below the x-axis, so it's going to cross, pass through the x-intercept, and then we'll have a turning point. And from 6 to infinity, the graph is going to be above the x-axis. So that's an idea of the graph. And this is going to be the last example. Number 42, we have the same questions. We are going to graph the polynomial function. The nice thing about this one is that it's already in factor form. Okay, so we're going to graph the function. Okay, so it's nice that f is already in factor form. So that's already in factor form. We already know the zeros. So the zeros of this polynomial function are going to be -1, 0, that has multiplicity 2, and 3, that has multiplicity 3. So we know that at the 3, the graph is going to wiggle, and at 0, the graph is going to bounce. Okay, knowing the zeros, we know the x-intercepts. The x-intercepts are going to be -1, 0, the origin, and 3, 0. And the y-intercept is going to be the same as the x-intercept. So since f of x or f of 0 is equal to 0, the y-intercept is also an x-intercept, or the graph passes through the origin. That's a polynomial of 6 degree, so we know the end behavior. The degree of the polynomial is the sum of the multiplicities, and the multiplicities are 1, 2, and 3. And the leading coefficient is 1. So the leading coefficient is 1. So the end behavior is going to be rising to the left and rising to the right. So we have from the zeros, we have 3 test intervals. The zeros are -1, 0, and 3. So the test intervals are -infinity to -1. So those are -infinity to -1, -1 to 0, 0 to 3, and 3 to infinity. We're going to make a table to determine whether the graph is above or below the axis. So we're going to make a table with the interval, a test value inside that interval, the sign of the function at that test value, or the function at that test value, the sign, and whether the graph is above or below the x-axis. Okay, so the intervals are those, are -infinity to -1. -infinity to -1, -1 to 0, 0, 3, and 3 to infinity. And if you remember, the function was x squared times x minus 3 cubed times x plus 1. Okay, so the first test value, let's take -2. At 2, the function is going to be 500. That is positive, and the graph is above the x-axis. At -1, 0, our test value is going to be -1/2. At that point, the function is going to be approximately -5.4. So at that value, the function is negative, and the graph is going to be below the axis. Or 0, 3. Let's take 1 as a test value. At 1, f at 1 is going to be negative 16, which is also negative, so the graph is below the axis. And 3 to infinity, the test value is going to be 4. F at 4 is 80, and the sign is positive. So the graph is above the axis. Okay, so now we can sketch the graph. I'm not so sure about the y values, but I definitely know the intercepts. So I know that the graph passes through the origin, through negative 1, 0, and through 3, 0. And from this chart, from this table, we know that on negative infinity to negative 1, the graph is above the x-axis. Negative 1 is a 0 of multiplicity 1, so that's going to cross. 0 is a 0 of multiplicity 2, so the graph is going to be below the x-axis. So it's a 0 of multiplicity 2 is going to be below the axis. 0 of multiplicity 2 is going to touch the origin and then become decreasing again. And 3 is a 0 of multiplicity 3. So it's going to do this. And at 3, the graph is going to level off and cross. And this is it. So I have finished the section on polynomial functions. The last 2 sections were about polynomials. So the last section of this chapter is going to be about rational functions. Thank you for listening.